Okay, so good morning everyone and welcome back to your second lecture of Computer Networks CS307. In this second lecture, we are going to cover network core and certain network parameters which help us or which aid us in monitoring the network condition. We'll be covering topics such as packet switching, circuit switching, and the overall network structure. And in addition to that, we'll also cover section 1.4, which is about packet delay, packet loss, and throughput or bandwidth in computer networks. So let's start off with the network core. The core of the network is a mesh of interconnected routers. These routers can belong to the same organization or these routers can belong to different organizations. The interconnection of these routers in a mesh or in any other way basically facilitates communication between networks that belong to different providers, different service providers, different organizations, and different companies. There are two terms that can be used to describe the operation of the network. The very first term is called packet switching. What actually happens in terms of data transfer within the core of this network? That is, the routers that basically interconnect with each other. The basic concept behind packet switching is that a host breaks down application layer messages into much smaller pieces called packets, and then these packets are forwarded from one router to the next across the links on the path from the source to the destination. The source and the destination can be a client computer, a web server, etc. Each packet that is transmitted at the full link capacity. Okay. So the important idea to take from this is that your core is basically a set of interconnected routers that are interconnected via links. Whenever you want to transfer data across these links, you can use something called packet switching technology. And in packet switching technology, your end systems basically break down a larger message into smaller pieces called packets and then forward these packets from one router to the next. That is all the routers in the path between the source and the destination. Packet switching uses a store and forward concept. So as soon as a packet arrives at a router and intermediate router, it is stored and then it is processed onto the next link. In this particular example, you can see that you have a computer or laptop on the left side. It has basically broken down a larger piece or a larger message into three smaller pieces, which are called packet number 1, 2, and 3. These packets are basically bits of information. So these are just bits that need to be transmitted to the intermediate router. Once all the bits of packet number 1 have arrived at the intermediate router, the intermediate router can afterwards forward it to the destination computer. Okay. So we basically store all the incoming bits of each of the packets. Once the complete packet is received by a router, only then it starts forwarding it to the destination on the next link. How long does it take to basically process this information? Depending on the transmission rate or bits per second and the size of the packet, which is in L bits. Okay. And we discussed this idea briefly and we derived the equation L divided by R as the total delay in the previous lecture. So it is going to take L divided by R seconds to transmit or push out L number of bits of a packet into a link at a transmission rate of R bits per second. It uses store and forward. So entire packet or all the bits of the packet must arrive at the intermediate router before it can be transmitted. Once the bits start arriving, we have internal buffer in the router. That buffer is just a piece of memory that is going to get filled by that particular packet. And once all the bits of that packet have been received, we can forward it onwards to our destination. So what is the total delay involved over here in terms of transmitting the packet all the way from the source to the destination? Okay. The total amount of delay that is involved can be calculated by adding the propagation delay over each of the links of the network. So in this present case, it is going to be L divided by R for the first link between the client and the router, and then an additional L divided by R between the router and the end destination or the end computer. We have a one hop numerical example for this particular scenario. So over here, let's suppose that the size of the packet is 7.5 megabits. And one thing that you guys should remember is that whenever B is written in lowercase, it basically means bits. Whenever by convention B is written as capital in computer networks especially, it means a byte. Okay. So over here, the L, which is the size of the packet, is 7.5 megabits, and the transmission rate R is 1.5 megabits per second. Then how long does it take to basically transmit the packet, let's say packet number 1, from the source to the intermediate router? That is going to be L divided by R. So on the first hop or on the first link between the source and the router, the total transmission delay is going to be 5 seconds. And then on the next link or on the next hop or on the second hop, let's say, we are going to add or we are going to calculate or compute the total delay once again. So that is again going to be L divided by R. So it is going to be 5 seconds plus 5 seconds. So in total we can assume that it is going to be around 10 seconds before packet number arrives from the source all the way to the destination. Okay. So we can derive a general formula from this as well, that depending on the number of hops and provided L and R remain the same, for n number of hops, you can have a total end-to-end delay of n multiplied by L divided by R. So this is one more example, and this is typical packet switching where two different end systems A and B are sharing the same router. The transmission rate over here is 100 megabits per second. As soon as the packets from A and B, which are color coded as blue and orange, start arriving at the router, they start getting queued, or they start getting fed into the buffer inside the router. The link between the router and the other routers which are connected to end systems C, D and E has a transmission rate of only 1.5 megabits per second. So in this particular scenario, because of intermediate queuing at the very first router, and because a link is being shared between two different systems, the overall transmission rate decreases, and thereby the total amount of delay in transmitting a packet from the source to the destination increases. If the arrival rate, which is given in bits per second, to the link exceeds the transmission rate of the link for a period of time, then packets will start queuing and they will need to wait to be transmitted on a link. And in the worst case scenario, the packets can be dropped if the memory buffer fills up inside the router. So in this case, A and B are connected via two links to router via 100 megabits per second. So obviously the transmission time is quite less whenever we want to transfer data from A to the intermediate router or B to the intermediate router. But the output link from the router to other routers only has a transmission rate of 1.5 megabit per second. So traffic is coming in or arriving at the first router at a very high rate, whereas the traffic that is outgoing or that is being output on the link is being transmitted at a very small rate as compared to the arrival rate. Because it is outgoing at a very small rate, the memory inside the router or the buffer inside the router will start filling up very quickly. And in the worst case scenario, if we run out of the buffer space inside the router, then the incoming bits of the packets will be dropped off due to buffer overflow, and that is termed as packet loss. So excessive queuing and excessive buildup of queues as a cause of low transmission rate on the outbound link can lead to packet loss, as well as a substantial delay in transmitting a complete packet between the sender and the receiver. We have to understand that the network itself, the core network or any network, has two fundamental functions. The very first one is routing. Routing determines the source to destination route taken by packets. This source to destination route is determined by something called a routing algorithm. So if you look at the figure below, you have one router connected via link number 1, 2 and 3 to multiple different routers. As soon as a packet arrives on this incoming router, need to decide which particular output link is going to be used to, let's say, transfer or transmit this packet onto the destination. So we have a choice of using link number 1, 2 and 3. Who is going to determine what particular link is going to be used? It is going to be the routing algorithm running inside this router. It could be something like shortest path first. It could be something like any algorithm that considers the number of hops or the number of intermediate nodes between the source and the destination as a main criteria for determining which link to use. So the definition of best route or best path determines is based on the metric that we are going to use to basically determine what is best. Is it high bandwidth, a link that has very high bandwidth compared to the others? Are we going to select that link? Is it going to be the total distance between the source and destination based on the number of intermediate routers or nodes? Is that going to be a criteria? So depending on the routing algorithm, we can determine which particular link to use to output the traffic from this router via link number 1, 2 and 3. So the first function of your core, the network core or these routers, is to determine the best available path between the source and the destination. That is, which output link to use. The routing algorithm is running individually in all of these routers, and these routers exchange routing information with each other about all the destinations or all the hosts that are connected to this network. The second key principle or function of this network or these routers is to forward traffic. Basically move the packets from the router's input to the router's output, as we have considered previously in the prior slides. An alternative technology to packet switching is called circuit switching. In circuit switching networks, the end-to-end resources or links are allocated to be reserved for the duration of the call between the source and the destination. So in this particular diagram, you can see that each link has 4 different circuits, or each path has 4 different links. In the example shown, you can see that the call between the top left and the bottom right computers takes on the path of the second link on the first strand and the path of the first circuit in the second strand. So over here, you can see that the information is arriving at this router from this particular computer, and this router basically establishes a circuit using this second link between these two routers. This router establishes another link using the first circuit between this router and this, and eventually the data is moved to the actual computer. Now the resources, this particular link or this particular circuit, number 2 over here and number 1 over here, is basically fixed for the duration of the session, for the duration of the call of data transfer. Whether the computers are actively exchanging information with each other or whether they are sitting idle, as long as the connection has been established, no other computer over here, say for example this computer, can transfer data using the first link. So this is basically a dedicated line between the sender and the receiver, and there is no sharing of this particular link. Now because there is no sharing, so obviously the number of resources needed to connect any two end systems via a circuit switching network is directly proportional to the number of devices that are actively transmitting and receiving on that particular network. Because each of these paths has four different links, so we can safely assume that if we are using circuit switching technology, then at any given time, a maximum of four computers or four end systems can communicate with each other and no more. This kind of a setup is a very typical or traditional setup that is very popular and used to be the primary technology or the main technology that was used in old public switched telephone networks. How is circuit switching accomplished, or how can we improve upon the previous example? We have two different solutions to add more users to the network. The very first one is called frequency division multiplexing. In frequency division multiplexing, we can use the same circuit to send traffic between multiple different end systems, but each one of them is going to be transmitting data at a different frequency. So if you look at this color coding scheme, we have four different colors and we have four different frequencies. So each pair of end systems can agree to use a different frequency for transmitting data over the same shared link if we are using circuit switching. In the previous example, we had a maximum of four users because we had four circuits within the diagram. If we want to add more users, then we need to allocate them different frequencies so that they can transmit at different frequencies, and then we can maybe increase from 4 to 8 users who are still using 4 circuit switched links or 4 virtual circuits. The second main technology that is available for sharing a circuit switched network is called time domain multiplexing or TDM. In time domain multiplexing, instead of changing the frequency of transmission, we basically allocate fixed time slots for each pair of end systems to transmit data to each other. So let's say we have one single link which is connecting four different computers on either side. So in total we have 8 computers which are sharing the same link, 4 on each side of the link. Now how can we share this link? We can either use frequency division multiplexing, in which case we are going to allocate a different frequency to each sender and receiver pair. And in the second case, in the case of time division multiplexing, we can fix time slots that in the first 5 seconds, only the first pair of computers can transmit. In the next 5 seconds, only the second pair of computers can transmit. Next 5 seconds, the third pair of computers can transmit and receive. And finally, in the following 5 seconds, the last pair of computers can communicate with each other. So if we have 4 different time slots, we can share the circuit according to these time slots between 4 pair of computers, that is our 8 computers in total, 4 on either side of a link. So these are two of the complementary technologies that basically enable us to add more computers or more end systems to a circuit switched network than is typically allowed by the circuit switching network. Because in a typical or traditional circuit switching network, you need to have only or at least one link between each pair of sender and receiver. If you want to add more end systems, you need more links because each pair is going to use a dedicated link. But that is not an economical solution. Therefore, in order to share the same link between multiple end systems, we have the feasibility of using either frequency division multiplexing or time division multiplexing. Then we need to compare which one is the best of the two, packet switching or circuit switching. Obviously, circuit switching is let's say more primitive technology, and although we have FDM and TDM, it does not compare with packet switch networks. Take the example of n users which are connected to this router over a 1 megabit per second link. Each user, when active, can simultaneously transmit, and they will get at least 100 kilobit per second. But in everyday computing and whenever we are browsing the internet, there is idle time as well. There are times when we download a page and we are reading the page and we are not actively browsing the internet. During those durations, we are not using the internet or we are not using the link. If we are using packet switched networks, that means that during that particular time, somebody else can use the link and achieve a maximum of 1 megabit per second. If all 10 people are using it simultaneously, obviously it is going to reduce. But because the probability of using the internet, that is the active time in using the internet, for each user is quite low. That is why packet switching supersedes circuit switching. Because if we were using circuit switching in the traditional form, we can only have a maximum of 10 users. And we are going to dedicate the resource that is at least 100 kilobits per second for each of these 10 users. But if they are only transmitting at 10% of the time, then that means that we are wasting resources. That is, we are wasting at least 100 kilobit per second whenever that user is not transmitting or receiving. Whereas in packet switching, you have several users that are going to share the same link, but because the probability of use is different, so it is quite likely if, let's imagine, 9 people are not using the internet, the 10th person is actively browsing the internet, they can avail a maximum of 1 megabit per second. And if 5 people are using it, you can simply divide 1 megabit per second by 5. That is the amount of data each one of them is getting. Still, it is a much better deal as compared to circuit switching because you can transmit a lot more data and still achieve a good transmission rate with packet switching as opposed to wasting resources with a circuit switching network. So is packet switching the main winner? It is great for bursty data. Bursty data basically means that we send out a chunk of data and then we do not send out any data at all, which is the behavior of our network related applications. It enables us to resource share. It is much simpler because there is no call setup. Whereas in circuit switching network, we need to basically establish or fix a circuit for a particular time between the sender and receiver, which is called the call setup time, before you can start transmitting data between the sender and receiver. Excessive congestion is definitely possible. Excessive congestion is a direct result of oversubscription. Oversubscription basically means that we have 100 megabit per second link between two routers, but that is being shared by, let's say, 1000 users. Then the probability of use of each user goes up. And when the probability of use goes up, that means that people are competing for the same resource. This can result in packet delay and packet loss. And in order to achieve or in order to circumvent packet loss, in order to deal with the packet loss due to buffer overflow, we need certain protocols in place. And a primary example of the protocol that we use to deal with packet loss or recover from packet loss is called the TCP protocol or Transmission Control Protocol that we are going to cover in chapter 3 later on. How can we provide a circuit-like behavior or a circuit switching behavior with a packet switch network? One way of doing this is by allocating resources or bandwidth guarantees for individual applications such as audio and video applications. So if 10 people are sharing the same packet switched network, we can tell the network or we can tell the routers within the network that if this is a audio or video related network traffic, then it takes priority over any other form of traffic. Or we allocate fixed bandwidth on the output and input ports of the router that we are going to have this much amount of data that is dedicated, or this much amount of bandwidth, let's say, that is dedicated for only audio and video sender and receivers. This is an ongoing problem if we come across advanced networks or if we delve into advanced networks later on by the end of this course. You will see that a lot of these examples are available in chapter number 7. Quick question for you, or let's say a brain exercise for you guys is to try to determine the human analogies of reserved resources. What can be a human analogy of circuit switching versus on-demand allocation or packet switching? Try to take an example or a case study from the university, from your everyday life, in which you are reserving resources, but some of those resources are getting wasted because there is no need for them at certain times. Versus on-demand allocation, that you allocate a resource only at that time when it is needed, and then you leave the resource empty for other users, for other students. So try thinking of something interesting in terms of the network, in terms of the applications that you guys have developed, or generally in everyday life. Okay, a quick indication that I give people, or a hint that I give people, is to talk about or think about the amount of people or the number of people, let's say, in the cafeteria at any given time, and they are queuing up and they are waiting for their food. How does reserved resources help them? And if resources were not reserved, what is on-demand allocation? So what is the existing format of getting food from the cafeteria? Would you suggest that this is similar to circuit switching, where resources are reserved, or is it actually on-demand allocation? So think about something interesting in terms of reservation of resources that you can later on map onto networks or network traffic. The structure of the internet. Like we explained before in the previous lecture, it is a network of interconnected networks. The end systems connect to the internet via access ISPs or internet service providers. These are the smallest form of internet service providers or very small companies which operate at a local level or at a country level. They provide internet services to residences, companies, universities, etc. The access ISPs in turn must be interconnected together by other internet service providers so that any two hosts that are connected to different internet service providers can transfer packets amongst each other. The resulting network is a little bit complex, and the evolution of that is determined by the economics as well as national policies. So say for example, take the example of PTCL, which is providing internet services over here. When we connect our local internet service provider PTCL to a global internet service provider, let's say level 3, or you can take the example of Etisalat or other such companies, then what determines which particular internet service provider we are going to use? First of all, the cost of that internet service provider, and secondly, whether we are going to trust that internet service provider. So we are not going to route it or basically transfer or receive traffic from regional or continental internet service providers that we do not trust because of our national policies. So let's take a step-by-step approach to describe the internet structure. The question is, you have given millions of access internet service providers. Now, how do we connect all of these access ISPs together? If we connect each one of them with each other, then the complexity of the system arises because this is a complete mesh. So it does not scale well economically in terms of the cost, and frankly speaking, this is just not possible. So how are ISPs connected to every other ISP? We have one global ISP or multiple different global internet service providers, and all of your access internet service providers basically connect to this central internet service provider. A very simplistic example. In this example, you only have one global ISP, whereas in reality, you can have multiple different global ISPs, and then they can be connected with each other as well. So this is an example of your three internet service providers A, B, and C, which are large continental internet service providers, which in turn are connected to country-wise or national internet service providers. These large internet service providers can connect with each other through special gateways that we call Internet Exchange Points or IXPs. In addition to the access networks, which are, let's say, national or country bound, we can also have regional service providers. Say, for example, for the EMEA region, Europe, Middle East, and Africa. Maybe for the Africa region, for Eastern Europe, for Western Europe, you can have regional internet service providers as well, which in turn again connect to global internet service providers such as ISP A, B, and C. How do global internet service providers connect with each other? Through Internet Exchange Points or IXPs, which are specialist gateways. So this is your network of networks and this is your global internet structure. In addition to the internet service providers, which provide you access to the internet, you also have certain content provider networks. Say for example, Google search services. Google is going to have presence in regional internet service providers, let's say, so that whenever you want to type something or whenever you open up the Google web page, the Google web server that is associated with your particular region displays you the web page or the Google web page for that particular region. When you open up something like Netflix, Netflix is going to give you the Pakistani or the local flavor of the services they are offering in your country. So the selection of the movies or videos or documentaries is going to be different from what they are offering in the US or in Western Europe. So in addition to these internet service providers, there are content provider networks as well. These are specialist companies which not which do not provide the access to the internet, but which are related with the internet service providers and provide certain type of content to the end users. So this is your network of networks. Now you have tier 1 ISP. Tier 1 basically means that it is a very large service provider, which we have termed as global service provider previously. Then you have the Google Web Services as well. Google is such a big player in this market, in the internet infrastructure, that they have their own internal network that can be directly connected to global internet service providers as well as to internet exchange points, which in turn are connected to regional internet service providers and which in turn are connected to access internet service providers. So tier 1 commercial ISPs, example level 3, Sprint, AT&T, NTT in Japan. These provide national as well as international coverage. And then you have content provider networks like I explained in the previous slide, for example, Google, Netflix, Microsoft, etc. These are private networks that connect directly their data centers to the internet. So they bypass your global internet service providers if they want to basically streamline and customize the services they are providing for your region and bring that service closer to the end user. This is an example of Sprint network in the US. Okay, this is directly copied from the book. We have a point of presence or POP that is available or present in all the major cities of US. We are talking about this service provider Sprint. So you can see from this particular diagram, the bottom three routers at each point of presence are basically connected directly to the customers. These are your access routers or access ISP network. In turn, these are connected to backbone routers. Okay, so we have a hierarchy at each of these points of presence. So the access routers are connected to backend routers, the backbone network, which in turn is connected to other backbone networks. And that basically creates a very big or a giant network in this particular for this particular internet service provider. If we take the example of your university, then how are we connecting to the network? A similar example would be that we are using two different types of internet connections. The very first one is provided by the government, which is the PERN network, PERN, which is Pakistan Educational Research Network, that is provided by the HAC. So you can connect to the internet via the PERN network, and that is obviously free of charge. That is provided for all universities across Pakistan. And in addition to that, your Wi-Fi system or your Wi-Fi access points use something like a PTCL based connection, okay, to connect to the internet. So you have two different networks which are being used in the university to connect you to the internet. So the routers, the access routers for each of these networks are different. All the access points connect to one access router, whereas all the local area network cables end in a different router. The local area network, the wired Ethernet connections, they connect to the access router. The access router in turn connects to the PERN network. Whereas all the wireless access points, they also connect to an access router, but that access router in turn connects to a router or a gateway that is provided by ETCL. So that is just a simple analogy of how you can have different points of presence or different internet service providers that are providing their services to the same organization, okay, to benefit the end users. Next, we will take a brief look at section 1.4. This is going to be about delay, loss, and throughput in computer networks. We briefly discussed queuing before. How do packets queue up inside the buffers in the router? If the packet arrival rate to the link exceeds the output link capacity, whether it is just momentary or whether it is permanent, then that basically means that a queue is going to start building up inside the router. When packets are queued, then they need to wait for their turn before they can be sent on the output link of the router. The amount of time it takes for the individual packet or the bits of the packet to wait inside the router before getting transmitted contributes to the delay that is experienced in sending a particular packet from the sender to the receiver. In extreme circumstances, if the output or the packet arrival rate is very high as compared to the rate of the output link, then there will be massive queuing inside the router, and the buffer might run out of space, which is called buffer overflow, and eventually that will result in the loss of that packet. What are the different types of packet delays? There are four different types of packet delays in total. The very first one is called the nodal processing delay, or simply processing delay. This is the amount of time it takes for the CPU inside the router to basically pick a packet on the incoming port and process it. That is, look it up where the destination is and how to forward it. So this is your processing delay. Next comes the queuing delay that we just discussed. The amount of time that a particular packet or bits of a packet have to wait inside a buffer before it gets transmitted. Third type of delay is transmission delay. The amount of time it takes for us to empty the buffer, that is, take the bits from the buffer and put it on the output link or the output port. That is called the transmission delay. The delay that we covered in the previous example, and we covered a numerical for this as well, where we derived L divided by R, is actually your detransmission or transmission delay. And then finally you have the propagation delay. This is the physical distance. Okay, the bits are traveling at the speed of light. Obviously they are electrical signals. Depending on the distance between the two routers, you can determine the total time it takes to basically deliver the packet or the bits of the packet between the two routers. That is termed as propagation delay. This is calculated by dividing the total distance between the routers, let's say d, by the speed of light, which is s. So d divided by s will give you the propagation delay between these two routers or any link. When you combine all of these, or when you add up all of these individual delays, that gives you the total delay in transmitting a packet from source to a destination. So like I explained before, the transmission delay is determined by L divided by R. The propagation delay is D divided by S, where D is the length of the physical link and S is the propagation speed, which is generally taken as 2 multiplied by 10 raised to power 8 meter per second. Remember the difference between the two. The transmission delay is the amount of time it takes the router to basically pick all the bits of the packet from the internal buffer and put them on the output wire. Whereas the propagation delay is the amount of time it takes for those bits that have been output on the wire to travel to their destination. This is your queuing delay, a very brief graph. Okay. R is the link bandwidth in bits per second, L is the packet length in bits, A is the average packet arrival rate. Now, if you have a function such as LA divided by R, if it approaches 0, it basically means that your packet arrival rate matches your transmission rate. Okay? That is, L and R, or let's say rather A and R, are almost similar. This will result in zero queuing delay or close to zero queuing delay. As the arrival rate starts increasing, that is A starts increasing, the product of L and A when divided by R starts to increase as well. And as the arrival rate is more than the transmission rate R, so you will have queue buildup inside the router. Larger the arrival rate or larger the difference between the arrival rate and the smaller transmission rate, we are going to have greater queues build up inside the router. So you can see the graph that as LA divided by R starts increasing, which is also termed as traffic intensity, your average queuing delay also starts to rise. Now, can LA divided by R exceed 1? Okay. In an ideal scenario, it can approach 1, but it generally will not exceed 1. Why? Because with excessive queuing delay, the buffer inside the router is filling up. After a certain time, instead of queuing further packets, incoming packets will start getting dropped due to buffer overflow. So that is why the traffic intensity can reach close to 1, but it usually does not exceed 1. The reason is that at that point in time, your buffer starts overflowing, so all the incoming packets get wasted. So the arrival rate or the effective arrival rate basically is stagnant at that maximum point. Okay. And beyond that, whatever packets are arriving, they are basically getting lost or they are experiencing buffer overflow. Okay. What are the real internet delays? How do we measure these delays? Okay. We use a program called traceroute. It provides the delay measurement from the source to the router along the end-to-end path between any source and destination. It uses a protocol called ICMP or Internet Control Message Protocol. Using this ICMP, you can basically probe the number of routers or intermediate routers between yourself and the destination. And you can also calculate the amount of delay that a particular packet is experiencing on each of the hops or each of the links between all of these routers. Traceroute can be used by the command trace-rt or it can be used as traceroute depending on whether you are using Windows or whether you are using Linux. So make sure that you try to find out yourself which particular version or which syntax is used for which operating system. The syntax is typing traceroute or trace-rt space and then any web server such as www.google.com and pressing enter. The result is going to be all the hops, intermediate hops between your client computer and the destination web server, and how much time has been elapsed on each of the individual links between yourself and the destination web server. This is a typical example of traceroute. So this is given in the book. You can see that as soon as you type traceroute to the CS web page of University of Massachusetts or YourCom France, you will get similar kind of output. Okay, for each of these 19 different hops, that is the 19, let's say, for the sake of simplicity, 19 different nodes or routers between yourself and the destination web server, you get three different delay measurements. Okay, so in the first case for CSGW, which is your gateway, let's say, you get 1 millisecond, 1 millisecond, and 2 milliseconds. Then for the next one, the University of Massachusetts gateway, you get 1 millisecond, 1 millisecond, and then 2 milliseconds. And then internally, among the other routers, you can see how much delay has been caused. So we get three different readings. Okay. When you look at the readings, you will suddenly see that at certain points, the delay is going to increase substantially. Those are the links which are intercontinental links. Okay. So in this particular example, if you look at number 7 and number 8, up until UC8, this particular router, which is termed as UC8.edu, this is, by the way, New York City metropolitan area and Washington metropolitan area router. Okay, you were getting 22 milliseconds, okay, or 22 generally overall. Whereas at number 8, once you connected to 62.40.103.253, this is the IP address of that particular next hop router. Okay, it suddenly jumped. The delay suddenly jumped from 22 milliseconds to something like the order of 100 milliseconds. So 104, 109, and 106. Where were we pinging from? We were pinging from the US, okay, which is your computer science department and University of Massachusetts, to a French server, the Eurocom server. So up until the number 7 hop, where you hit the gateway of New York City metropolitan area, the delay was the order of tens of milliseconds. Suddenly at number 8, once you crossed the Atlantic, the actual delay increased to hundreds of milliseconds. Okay, so this is a quick way of identifying which of these links is a transoceanic link or an intercontinental link. And then from there onwards, you can see that it went to DE21, which is Germany. Then FR1, the traffic entered a French router, and then it got passed on between 10 and, let's say, all the way to 16 among different regional or access internet service providers in France, and finally at number 19 it arrived at fantasia.yourcom.fr, which was your destination web server. At number 17 and 18 you can see that there are asterisks. Okay. So it is not clear what is the name or the IP address of these routers. Either the probe was lost, that is when you were pinging or trying to trace route at number 17 and 18, either the reply was lost or the administrator of that router has disabled any kind of response that is going to identify the router either by its IP address or by its name. So that can be a security precaution as well. But the traffic was forwarded by the routers at number 17 and 18, and eventually it got to number 19. But our traceroute application did not give us the name or the IP address of the routers at 17 and 18. Why? Probably because the reply was either lost or it was administratively disabled. That is, the underlying protocol for traceroute, which is ICMP, Internet Control Message Protocol, was disabled administratively on those routers by the network administrator, purely for security reasons. Coming to packet loss now, because of excessive queuing, like I explained, you can have buffer space filling out. Okay, this is your waiting area for incoming packets. And if the arrival is quite high as compared to the output, then you are going to have, or you are going to run out of this waiting area or buffer space, and eventually your packets will start dropping. The lost packets can be retransmitted once again by the originator or the sender. But in order to do that, you need to have another protocol in place, such as TCP protocol, which can identify at the destination which packets were expected and have not been delivered, and then request either A or B to resend those lost packets once again. Finally, what is throughput? Okay. Throughput is the rate in bits per a time unit like seconds or milliseconds at which bits are transferred between the sender and the receiver. It is instantaneous. Okay, so if you ping www.google.com right now, you can see how much time it takes to actually get to the Google web server and receive a reply, and it will give you an indication of what bandwidth is available instantaneously at that point in time. The bandwidth that is available in real time at that particular instant is basically the throughput of the network. When you calculate the average, when you test it multiple times, you can calculate the average value of the bandwidth that you are getting at those particular timestamps, and that gives you the average throughput of the network. So over here, the server sends bits into, let's assume that this link is actually a pipe, and it can carry the information rate at RS bits per second, whereas the second pipe can carry it at RC bits. So if there is a mismatch between RS and RC, then how much amount of data can be transmitted, or what is going to be the effective throughput? Let's suppose that RS is less than RC. What is going to happen then? What is the overall throughput of this system? Or how quickly can we transmit the data? The answer is that the effective throughput is going to be RS. If RC is less than RS, then the effective throughput, or the amount of data that we can send from the server to this client computer, is limited by RC. So the slowest link within any given path from the source to the destination is basically your effective throughput. Okay, the slowest link in the path between the server and the client computer, that is your effective throughput. So this is your more comprehensive example. What is the average end-to-end throughput if RS is less than RC? If RS is less than RC, then we can only transmit at a maximum of RS. It does not matter whether the size of RC is greater. Why? Because we are getting throttled by RS bits per second. Okay. And if RS is greater than RC, that means the size of the link RS is greater than RC. So you can transmit more data in RS, but it will get throttled as soon as it gets to RC after crossing the intermediate router. So the effective throughput is basically dictated by whichever link in the end-to-end path has the slowest transmission rate. This is another example. So this is slightly more complex, in which you have RS, the transmission rate from the server to a central link, which is R bits per second, which in turn is connected to three more links at RC bits per second. We can safely say that the middle one is being equally shared among all of these servers. So which is the bottleneck? Depending on whether it is RS that is smaller than RC, or RC is smaller than RS, or whether R is smaller than RS and RC. The slowest link in the path is basically the effective throughput between the sender and the receiver. And in practice, it is usually the access link, RS or RC, that is going to be smaller than the backbone link, which is R. So that basically brings us to the end of the second lecture. Please go through the slides once again and the handouts that I have provided. And if you have any questions, then write them down and do a bit of exercise yourself as well in terms of understanding packet switching and circuit switching. Thank you.